video tutorial series on how to use GreenScenario. In this episode, we will be looking into another workflow, and this will be how to size our detention elements to meet the local requirements. So when you look at the model currently, we have our stormwater service level at 0%. So essentially, we're not reaching any of the required volume. And it's also shown over here, detention volume. So when I click on that, detention volume is also at 0, and that makes sense. Our peak runoff coefficient right now is at 1. So essentially, all the water that hits our surfaces is going to be converted into runoff. So there's 0 infiltration or evaporation component to it. And mind you, this is our peak runoff coefficient. Our average runoff coefficient is shown over here. So this will be throughout the year. There is still the overwhelming majority is going to be converted into runoff. Some will evaporate. But during a heavy rain event, this is the peak runoff coefficient that we're looking at. Okay, so how do we fix that? How do we make sure that we're reaching our requirements? So first of all, we would need to introduce a detention basin component. So let's just put it here. Let's introduce just a rectangular swale and have a curve that represents that, and then we'll connect it over here and then add it to our drawing. So first the thing that you can notice is that our detention volume right now provided by the swale equals 11 cubic meters, and this translates to roughly 55% of the required volume. So what we can do is obviously we could try and increase the size of this whale. So either we increase its depth, or what we also could obviously do is just change its area and then while keeping the depth, and then we'll be able to see, okay, right now we need 100, or we are reaching 108%. So we could try and be a little bit more precise and then try to nail it exactly, or maybe just overshoot it slightly to have more precision over here, right? So we could change the geometry of the scale as well, hit our detention volume of 20 cubic meters and get 102% of the required volume this way. Very quickly, very intuitively, we have met the expectations. But maybe there is other ways of achieving the same value over here. So essentially the same stormwater service level with without necessarily changing the geometry of this whale and keeping this volume lower. And of course there is, and then so one of the possibilities over here would be for us to change the essentially the peak runoff coefficient. It's still at 1. And so what we can do is we could change the material of our landscape material, right? So around us, you see like we changed it to gravel, and then the peak runoff coefficient is automatically much lower, which also means that, so let's go back to asphalt, you can see with the detention volume of 20 cubic meters, we're reaching 100% of the requirement. If we just change the material, these same 20 cubic meters translate to 266%. So what it means is that our swale can now be so much smaller. So it can be roughly, probably 7 cubic meters. And now we'll be hitting 100% of the requirement. The reason for that is that we have lowered the peak runoff coefficient. So essentially there's less runoff that we need to detain in our detention basin component. Another way of lowering this peak runoff coefficient even more would be to look at our building over here and saying that rather than using a conventional roof, we could maybe work with an intensive roof, green intensive. And you can see it does affect our calculations as well. So here we are gaining another 10%, which would mean for the swale area that it could, or swale volume, that it could be around 6.5 cubic meters to reach the same stormwater service level. And of course, you could try and think of other ways of reducing this peak runoff coefficient even further, or maybe not reducing, but influencing it. One of the ideas would be to introduce a green area component. So let's just do that, and let's see what kind of effect does that have on overall calculations. And for example, if we were to go back to our asphalt, let's turn this one off for a second, so I'll disable it. You can see if everything is asphalt, we have 31%. If we turn it on, we have 32%. So it's not a dramatic and noticeable difference. But then if we were to increase the size of it, of course, it will gradually have a more and more of an effect. And the reason why there's multiple ways of addressing the same target over here is that it's a compound calculation, right? So it's looking at what is the peak runoff coefficient for the entire site, and how much water is hitting the site during our design rain event. And this one is controlled through our data input over here. Right now we're looking at 20 millimeters of rain, and it can correspond to, let's say, a 10-year event, 30-minute duration. But what if we wanted to analyze the same site for a, let's say, 50-year event and also 30-minute duration? And then we would look it up in our external tables and say maybe this is 28 millimeters of rain. And then we would see that with the same runoff coefficient and detention volumes, we're only reaching 28% of the requirement, as opposed to roughly 40% with a 20 millimeter rain event. So in this way, we again, it's very complex in a way that there's multiple factors playing into the equation, and there is no one answer to the question. And it becomes more interesting, or even more interesting, when we add the economics aspect to it. So for example, if we go back to our conventional rooftop for the building, we can see that the investment cost goes down to 61 euro per square meter. So let's try and maximize the swale area to reach 100%. So right now we have detention volume of 16 cubic meters, and we need to pay for that 60 euro a square meter to reach the desired stormwater service level. And if we wanted to change the roof to a green roof, and then we can see immediately, sure, our swale can be slightly smaller, but we need to pay for it more because intensive green roofs, they cost more than a swale does, right? So we're paying 68 euro per square meter. And by the way, the square meters are, or this, the price is translated to the entire project size. So our area over here is 1,000 square meters. So this is 1,000 by times 68, so it's 70,000 euro that we'll pay roughly for these measures over here, as opposed to working with a conventional roof and making this swale slightly bigger, and we will still be paying only 59 euro. And actually, over here, the bigger the swale is, the cheaper the whole project becomes, because we're actually cutting away from concrete or asphalt, and asphalt is more expensive than just our swale. So again, a lot of complexity in these calculations, and GreenScenario helps you visualize the whole process and understand the impact of individual components on stormwater service level calculations. And as with anything in GreenScenario, you can set these up as separate scenarios and switch between these and compare different options, and also set your baselines over there. And then while you're working on a particular scenario, you can be always comparing it to your baseline and say, oh yeah, so this is much more expensive than I can afford. let's go back, let's scale something down, and again compare it for different design rain events. Don't only look at the requirements. Maybe with very little additional investment, you can boost the design, the service level by maybe 20, 50 additional years of protection in terms of occurrence of these rain events.